Welcome back. In this lecture, in the context of a battery, we will look at the terms what we mean by theoretical capacity and state of charge. Battery is basically an energy storage device. So our notion of theoretical capacity should reflect this. And one measure of capacity is the energy stored that is measured in the units of watt hours. As you can see, this would amount to energy stored. Okay? So that's one way to depict the capacity of a battery. Battery is also used for supplying energy for a certain period of time. So another measure of capacity is the amount of charge stored in a battery, which is uh, depicted by ampere hour. Okay, so this would amount to um, giving a measure of charge that is stored in a battery. So the capacity of a battery, either by this measure or by this measure, would depend on the moles of active material present in the electrode of the battery. The active material is the anode and the cathode. So the moles of active material present would determine the capacity of a battery. So how do we know how much capacity is available once the battery is in operation? This is not a trivial question. We will elaborate this in a couple of slides. So let's first understand what is happening when the battery is getting discharged in terms of active material. Supposing we take a particular battery, zinc is one of the electrode and silver oxide is the other electrode. And these two electrodes are separated by a separator. So chemical intuition suggests that this material, zinc, would tend to get oxidized, and the oxygen for it to get oxidized, if it is supplied from silver oxide, if this oxygen is the one that is oxidizing zinc, the entire reaction of zinc getting oxidized to zinc oxide and silver oxide getting reduced to silver would be an exothermic reaction, and that is what gives rise to a potential of a battery. So when the battery is under operation, gradually zinc will get oxidized to zinc oxide, and silver oxide will get reduced to silver. So as the battery gets discharged, this reaction, that is zinc getting zinc oxide, that will increase, and silver oxide getting reduced to silver, that will also increase. These are all solid compounds with different densities. That is, zinc has a different density from zinc oxide, and this zinc oxide has a different density from silver oxide, and so on. Okay, so all four materials have different densities. Therefore, overall volume of the active material would change. So that is, if I start with a particular volume, let's say I consider this as zinc, and the separator, even if it's a liquid electrolyte, it's an incompressible um, a component here. And this is also a solid incompressible, let's say, as a first approximation. The overall volume of these three components would change as the battery gets discharged. So how do we measure the state of charge or the state of discharge, which is the opposite of each other in a battery? That's a non-trivial question. So first, let's define what we mean by state of charge. This is the available remaining capacity divided by the total capacity times 100%. Okay, so this is an important measure because we would like to know, as the battery is in operation, how much capacity is remaining in the battery. So the total capacity is measured by the active material present here, and as the battery gets discharged, the active material gets reduced in time. So yeah, so I mentioned that the volume of the cell changes during discharge. So whether it decreases or increases depends upon the density of the new material that's getting formed. All right. So why is state of charge a non-trivial issue? If I just measure the voltage of a battery, that really does not tell me the state of charge. Why is that so? So a battery is a constant potential source. What I mean by that is that when the battery is getting discharged, the useful part of a battery is in this regime. Okay, so in this regime, so when I start discharging the battery, in this graph, the y-axis denotes voltage, the x-axis denotes time. So as I start discharging the battery, there is a sudden decrease in the voltage of a battery, and towards the end life of a battery, there is a dramatic decrease in the voltage of a battery. But the useful lifespan of the battery is from this point to this point. Here, the voltage of a battery is more or less constant. So if I just measure, let's say, a battery voltage at this point, I cannot really know how much capacity is remaining in the battery. So typically, you do not want to be operating the battery in this regime. So you operate the battery only in this regime. You also okay. So that is the main part. Just the measurement of an voltage is not a measure of the state of charge. Okay, so there are a lot of important empirical techniques that are utilized in uh, indicating the state of charge. In different battery chemistries, the ways to measure indicate state of charge differs. Okay, so in lead acid battery, for example, there are some simple indicators of state of charge, which would be like, let's say, even if I measure the density of, it's an aqueous battery, if I measure the density of the electrolyte, that gives me a measure of state of charge. We will look at that in the next lecture. But in and in a lead acid battery, even if you expose it to atmospheric conditions, nothing happens. Okay, the battery components, the electrolyte is not combustible and so on. So, but in some other battery chemistries, there are not simple measures of state of charge. So this is an challenging issue. But right now we have just presented what exactly do we mean by state of charge. In the next lecture, we will look at cell potential characteristics of a battery using certain thermodynamic consideration. That's the topic of the next lecture. Thank you.